Good afternoon. I'm Arun Serafin, Executive Director of the Emerging Technologies Institute at the National Defense Industrial Association. I'm very excited for today's webinar, Quantum Technologies 101, with Dr. Pops Paparao, who I will introduce in just a moment. Quantum technologies are emerging as one of the most transformative areas of modern science and national security. Just as breakthroughs in microelectronics reshaped computing, advances in quantum information, sensing, and communications are poised to redefine how the U.S. develops and deploys next-generation defense capabilities. We're now moving beyond theoretical concepts into real-world applications that can enhance precision, security, and performance in ways classical technologies cannot. From ultra-secure communications to highly sensitive quantum sensors and early-stage quantum computing, these capabilities can transition from research labs into very practical defense use cases. Pops will also touch on the significance of the recent Nobel Prize in Physics awarded to 3 researchers in October for their 1980s work on quantum mechanical tunneling. This is a great example of how fundamental quantum research continues to accelerate innovation across the national security and broader technology world. Now, some administrative remarks before we get started. All attendee lines are muted. If you have a question during the webinar, use the question box, not the chat feature, please. You can ask questions throughout the presentation, but we'll be focusing on answering those questions at the end of the presentation. We are recording today's webinar for members unable to attend, and this webinar is just one of our continuing monthly series that you can track on our weekly newsletter. Now to introduce our speaker, Dr. Pops Paparao. Dr. Paparao is the Senior Director of Emerging Technologies and Research at New York Creates, which is a not-for-profit research, innovation, and commercialization organization based in Albany, New York. He obtained his bachelor's degree in metallurgical engineering from the Indian Institute of Technology and his PhD in material science and engineering from the Massachusetts Institute of Technology. He's worked in industry at Texas Instruments and at IBM Research, and since 2014, he's been in Albany, first with Sematech, and now with New York Creates when it was launched in 2018. At New York Creates, he leads work on quantum, neuromorphic, and energy-efficient computing, among other things, and he's obtained funding from a variety of sources, including the Departments of War and the Department of Energy. Pops, thanks for joining us today, and we really appreciate you taking us through the seminar.
Thank you. Thank you, Arun. Let me get my screen sharing going. All right. Could you just confirm that you can see my screen?
We can see it.
All right, great. Let me start by thanking Arun Serafin, Daniel Park, Sam Moyer, and Sierra Cherry for giving me this opportunity to talk with you about quantum technologies. And, literally to share my passion with you, because I like to say that my nightmares and dreams are composed of quantum. And as Arun said, it is particularly relevant now after the Nobel Prize was given earlier last month, rather, for seminal work that inspires our work, among others. So let me go on with, let me hide meeting controls. Okay, there we go. So going to the next page now, the first page, I want to take 2 seconds to introduce what NY Creates is. We are, I think, justifiably proud of the organization that I'm a part of. It's a world-leading R&D center, and we work on innovation, commercialization, and workforce development in advanced technologies. All of this is done in partnership with a variety of institutions, commercial, academic, national labs, and so on. And I will say, do think about visiting us. If you're not a US person, as in permanent resident citizen, you will need to go through a background check. And I will tell you that, as you can see from the cranes here, buildings keep popping up. So things keep changing as we seek to expand. Now, NY Creates is perhaps, as Arun said, founded in 2018, but we have a long history at the Albany Nanotech Complex going back to the last century. And so over these past 3 decades, there has been over $15 billion of cumulative investment. And there are over, 2,500 people on site working at a variety of companies from Tokyo Electron, which has its TEL Technology Center America headquartered there, Applied Materials, AIM Photonics, which is an American Manufacturing Innovation Institute that got started. Wolfspeed and Cree started developing their 200 millimeter silicon carbide work there. So over the years, we have continued to grow and expand and attract additional participants to the site. So the way in which we are helping this ecosystem grow is through state-of-the-art facilities, right? I mean, and so this is a bird's eye view again, where you can see NanoFab North, NanoFab Center, NanoFab South, and these are, when the site was first built, these were among the first buildings that were built, and then NanoFab Extension, it used to have the world's only and first, 450 millimeter silicon wafer effort, right? And now it houses, the EUV lithography tools that we currently have, and a whole bunch of equipment that is state of the art. This portion is also Applied Materials, Materials Enablement Technology Accelerator that is based here. Tokyo Electron has its Technology Center America based here. And in this new building, which is an artist rendition, it is in construction right now, should be finished in a few more months, is our NanoFab Reflection building, which will hold the first high-NA UV lithography that is not behind any corporate walls. And in addition to that, of course, there are a whole range of advanced 300 millimeter silicon wafer. I should probably take a second to explain. 300 millimeter is the size of the wafer, right? 12 inches, about a foot. And all the modern fabs, the latest fabs, use that wafer size of silicon because it is that much more efficient to get and cost effective. So at NY Creates, we are working, as I said, with partners to advance a range of technologies, so all the way from non-volatile memory technology used in neuromorphic computing. We worked with Wolfspeed Cree to enable their power electronics to leapfrog into the 200 millimeter scale. I'm working with various other faculty on nanobio devices. There is a strong heterogeneous and packaging integration center that we do, led by IBM, that we partner with. I mentioned AIM Photonics, which is creating a framework whereby people can participate in getting their designs fabricated at state-of-the-art tools, right? But the focus of today's talk will be our work on quantum technologies, or rather, that is why I'm here. The focus of the talk will be a survey of what quantum means for us now and why it means even more for us now. So, the Nobel Prize that was given earlier this year, Physics Nobel Prize, to John Martinez, John Clark, and Michel Devoret, recognizes that they did something that is crucial to all of the superconducting quantum computing that is happening today, right? And what is different and why it deserves a Nobel Prize is that we all think of quantum as something about the very small or very low energy, something you can't see, atoms, inside atoms, and so on. But what they demonstrated was that there is such a thing as macroscopic quantum tunneling, that this physical object, a superconductor, and a Josephson junction, that you see that with your naked eye, that entire thing has got a macroscopic quantum phase. And if you use a Josephson junction, then you can create these multiple energy states, that you can see these multiple energy states that are now utilized in quantum computing. So, and I want to promise you that there will be no equations in this entire presentation. I am not a physicist. I am teaching myself quantum as I go along. I'm a material scientist by training, as you know, as you heard from Arun. So, you and I are in the same boat. So we will approach quantum at a very elementary level without having to worry about Hamiltonians and so on. So our work at NY Creates is anchored by the work that the Nobel Prize given earlier this year honors, right? So here is an example of the Josephson junction that I mentioned there. We fabricate that using aluminum. We used to fabricate that using aluminum. We'll talk about what we're doing now later. But the idea is that this Josephson junction, the superconducting aluminum that is on either side of it, is the core, the heart of the Nobel Prize that was given. So in cross section, here's the transmission electron microscope cross section showing the tunnel barrier that separates one aluminum from the other aluminum, right? So that is the core. And of course, there are a whole host of companies that are pursuing the promise of quantum. This is the Sycamore chip from Google, where it's got 53 qubits that they have been demonstrating. Here is the IBM quantum computing package chip that they're talking about, where you've got the qubit layer, you've got readout layers, and you've got wiring layers all put into one package. And recently, you must have seen the announcement from IBM saying that they will be leveraging the 300 millimeter wafer fabrication facility where I work, so they will be using it for their purposes. So it is nice to hear that we are on the upswing of the hockey stick, if you will, where everybody is looking at scaling, right? That is the important thing. It is why it matters even more now is that the prior 2-3 decades of work have shown that we need to be tackling the problems of how to make quantum computing systems of enough size that it solves problems of interest to society, of interest to national security, and so on. Going on to the next thing. So when Arun asked me to present a talk about the quantum Nobel Prize, I was looking back and I created a chart for myself to say, what do the quantum related prizes look like over the past 100 years, right? And I must confess that I was surprised to see that as I wrote down each and every one of them, there was a continuous thread over the past century, right? I mean, all the way back to 1912. So there are a whole range of them. You'll recognize these names here: Planck, Einstein, Bohr, Schrodinger, and Heisenberg. These are from the early 20th century. And then, of course, here is the Josephson junction that was 1962, where the Josephson won the Nobel Prize. And then, of course, that Clark, Deveray, and Martinez demonstrated superconducting qubits soon after that, and they got the Nobel Prize for that. But the other point that you can see, if I were to color these dots in red for what is critically important to today's quantum computing, there is perhaps an acceleration and a thickening, if you will, or a quickening in that quantum prizes that have been given. So we will go through some of these, but what I want to say, the reason I highlighted some of these are that each one of these Nobel Prizes relate to a kind of quantum computing that is being explored by a whole range of companies and which is being scaled, right? So that's why these become important. There are other Nobel Prizes here, for quantum dots and so on, which are not directly relevant, but more about that in a second. So uh, let's take a sense to, you must have heard people use the term that we are in quantum 2.0. And if we are now in quantum 2.0, what is quantum 1.0 look like? And it goes back to the early days of quantum, right? Here's the Solvay conference from 1927 with Einstein, all the leading lights attending that conference. And of course, this we have all learned about the atom and the energy levels inside the Bohr atom. And this is an example of what was central to quantum at that time, right? They were able to say, okay, here's the Planck's constant. Here is the energy that is liberated when an atom decays from an excited state to a lower state. And then, of course, we've all heard about the Schrodinger's cat. Is it dead or alive inside a box? We don't know till we open it and measure it. Of course, there were a whole host of debates and arguments as to what this precisely meant, what is the nature of quanta, because it was new then, right? But what I want to say is that from the 1920s and 30s, going into the late 20th century, we started leveraging quantum in a way that is different from the way we're using it now. So every one of us has got, in our pockets, we've got billions of transistors in our cell phones. And the heart of that of the IC chip is the transistor. And this the conduction between the on and off state that we hear about in a transistor is accomplished through what's called an inversion layer, right? And this to be able to model that, to be able to understand that, to be able to design the chip so that it works as intended, you need to use quantum mechanics because the length scales here are very small. The description of all of these energy levels is also, a manifestation of quantum mechanical understanding of matter. We all use laser pointers, right? I mean, and the two states of the laser that the atoms decay from excited to non-excited state, releasing light that we create a laser in, is also leveraging quantum mechanics. And Professor Maungi Bawendi at MIT developed quantum dots, and soon after that, Samsung leveraged this quantum dot process to create an LED TV that is there in many of our homes. Not mine yet, but hopefully sometime soon. So, we are utilizing quantum, but what is quantum 2.0? Now, in quantum 2.0, this superposition of the dead cat and living cat is not a theoretical concept that you argue over a cup of coffee about what it means, but it is actually a physical resource. Think of, if in the early times of the Bronze Age, we suddenly discovered that we could mine copper, and use it for good effect. Now we are seeing that superposition is a physical resource that can be used for quantum computing. And then the other point is the entanglement is another physical resource. So, what is superposition? Just to repeat what most of you may already know, in a regular electronic bit, it's either one or a zero. It's either heads or tails. But in a quantum bit, a superconducting quantum bit, or any other kind of quantum bit, the the coin doesn't need to exist only in one state or the other. It can be in a superposition of all of these, any of mixture of these up and down states, using complex numbers in order to define the extent to which these two are mixed to each other. So it is a superposition of all of these states. The second weirdness about quantum, which of course, as we all know, Einstein called it spooky action at a distance, is that when quantum objects exchange energy and get entangled, they start behaving not as two different objects that are mixed up using laws of simple mathematics, but that it is actually a unitary entangled object that has unique characteristics of its own. So here, looking here, is an example, let's say, of two systems, which can be either circles or squares, and they can be mixed up um, amongst each other, system one, circle or square. And if you remember, this is kind of like the Punnett square in genetics, where you can say you take this and this, there's a 25% probability that, it'll be two circles from the two systems, and a 25% probability that it'll be this way, 25 this way, 25 this way, right? Just like mixing two genes in sweet pea. But the weirdness comes from the fact that when you entangle two quantum systems, they don't follow these probabilities. They actually show either 50% probability of both being circles or both being squares in this way. And so the part of the reason why I highlighted this source in big bold letters is that this is a very nice way to understand entanglement. Sorry, I did promise no equations, but basically you can say that the entangled state is a mixture of these two in two states. So, but this is a more intuitive way of understanding it, right? So once you have this, you can have these two states. This is another physical resource that is exploited. And what do I mean by exploiting? By exploiting, we mean that we can do real work. Here is a way in which this is a paper from McDermott and Mukhanov and others, where they're able to use microwave pulses to engineer that superposition to make it a mix of an up and a one exactly on this equator. Here is a picture that shows an ion qubit, ytterbium ion, that can exist in a mixture of two states, two quantum states, and an up and a down that is within the atom itself, right? And here it is how those entangled photons can be utilized. So you're able to utilize the fact that these two are entangled. If one is red, it must follow that the other is blue, and whereas if one is blue, the other must be red, right? So these are the physical resources that we use for doing quantum computation, quantum sensing, quantum networking, etc. We'll talk about that now. The other thing I couldn't help myself was to say that when we go to Quantum 2.0, the world is opening up in ways that one could not have imagined before. And this is from Professor Chris Monroe's talk that he gave at a seminar series that I run, where you can see that perhaps there is a similarity between a wormhole and a quantum entanglement, except one is on a galactic scale and the other is, of course, at a much more human scale, right? So, the implications for quantum in new areas of physics are increasing and numerous. There are people who are using quantum devices in order to understand the nature of dark matter, for instance, right? And dark energy. So the one thing that I racked my brains to remember who it was that mentioned this at a conference that I was attending, right? The first applications of modern computers, right? You remember this is from World War II and the ENIAC soon after that. The first applications were code breaking, right? The Enigma code, and then creating artillery firing tables, right? I mean, so, and the person who made the analogy said this was what we used the first computers for, and guess what we are doing with the latest quantum computers? One of the first applications that came along was breaking the RSA encryption that we all rely upon, that banks rely upon, where two very large primes are multiplied in order to create the code for encryption. So breaking RSA encryption, thanks to Shor's algorithm, is one of the first applications that people started talking about. And of course, the other thing is simulating nuclear physics, so that you don't have to explode a nuclear bomb in order to understand what is going on deep inside it, and design better devices and understand the high energy nuclear physics better than we currently do. So this is work that is actively being worked on, and in fact, I have the honor of being part of CTQA, where there are people that are working on this at Brookhaven National Lab. The just one small anecdote that I heard. I was sitting at an MIT Lincoln Lab conference where somebody said, "Well, back when Shor's algorithm was first came about, apparently there was a person from the NSA who got up and said." I'm from the NSA and we're interested in quantum and sat down and didn't say anything else over the next portions of the conference. But obviously now, all these decades later, the obvious applications of quantum for encryption and so on are well known. So what I'm going to do here for the next few slides is talk about the variety of qubit types. We talked about the spinning coin and the fact that it is not just heads and tails, it's spinning all around. You can be in a superposition of states. These two coins can get entangled with each other. But in physical terms, what can they be made of? And there are a whole range, and I don't think we will complete all the qubit types that people are working on. But I'll confess to selecting those that are closer to scaling to larger volumes, right? One of them is trapped ions. And what is amazing is that this is a picture, thanks to IonQ, where you can actually see individual ions being lit up and emitting light. And this is an ion trap chip that is being used to hold these ion traps. And people are this is from Lincoln Lab, where people are using photonic integrated circuits in order to be able to talk to these ions using elements that are present on a simple photonic chip rather than using whole big optical benches. So trapped ions, IonQ is among the companies. Quantinuum is another one that is working on scaling these up. And as you can see, you can count the atoms here. We are not talking a small number of atoms. They are also talking about whole arrays of atoms. There are neutral atoms in addition to the trapped ions that are being considered for quantum computation. The other kind of quantum computing is photonic quantum computing. In photonic quantum computing, you're using photons literally to do, the spin of the photon or the time bin or the frequency of the photon in order to do quantum computing. There are a whole host of, I mean, not as many as in other modalities, but two of the big companies working on photonic quantum computing are PsiQuantum and then Xanadu. Xanadu is based headquartered in Toronto. PsiQuantum headquartered in California. And they have two kinds of quantum computing. One is fusion-based quantum computing, where they are doing entanglement measurements. And then the other one is Gaussian boson sampling, and that is the system by Aurora. Different in the basic details, but both of them use photons, and you can see some of the similarities between their physical implementations. They all use Mach-Zehnder interferometers and single photon sources and photon detectors in both cases in order to sense the result of the computation, right? So you launch a photon, you make it do work through superposition and entanglement, and then you measure it, and you're able to determine what the result of the computation is. I'm keeping an eye on the clock. Yeah, good. We're in good time. The spin qubits in semiconductors is another kind of quantum system that has the advantage that it can leverage all of the technology that has been developed for semiconductors, because it is a special kind of a transistor that is being utilized to create the spin qubit. I don't want to go into the details of this one, but in one case there is a quantum dot, a single electron that is present in the semiconductor. Here it is silicon, or in this case it is a quantum well where there is a silicon layer sandwiched between two silicon germanium layers, and you create a single electron quantum dot there, and you are able to create a spin state for that one. Use that to do quantum computation using the spin as the quantum modality. So why is this scalable? Because right next to it, you can put in transistors, plain vanilla transistors, to allow it to control the silicon qubit and to read it out. Right. So that is the main reason why I think Intel is very active in that area. Dirac is a company that is based out of Australia that is working on that. And of course, they are working with companies in the US as well. Hughes Research Labs is the sort of, a basic research lab that has done amazing work in supplying the complex stacks that are required in order to grow, in order to make these devices, the silicon germanium quantum wells. And what is interesting is that the lady Lisa Edge, that is at HRL, was once my colleague at IBM at the same Albany nanotech complex where we currently work. The reason I'm saying that it needs isotopically defined silicon 28 is that, 28, this has because it is an even number, it has no net nuclear spin, whereas there are some isotopes of silicon that have silicon 29, one extra nuclear nucleon, and therefore it has a spin that can rob energy from the electron, and so you would like to make sure that you can get it to as low count as possible. Now, we've all heard about the fact that Majorana postulated back in the 1920s that there was this new state of matter. And over the past few years, Microsoft has announced that they can actually fabricate material devices utilizing that demonstrate the Majorana zero modes. How they do it is by creating a sandwich between a semiconductor, indium arsenide, and a superconductor, aluminum. And by sandwiching them together, and being very careful about the interfaces and so on, they're able to create this topological superconductivity state. They call it a topoconductor, and which has, because it is physically separated, this odd and even modes are separated by physical distance, it is less prone to error than other kinds are. The I shouldn't say this is last but not the least, but I'm particularly partial to superconducting qubits because that forms the bulk of my work. The reason I picked some of these pictures are you can see the macroscopic state of the quantum device that I was telling you about. Here's a readout resonator, coupling resonators. All of these are superconducting, and they are pretty big, hundreds of microns. Here is a similar device from ETH Zurich, where you can see they have 17 qubits. And again, it's a huge device that occupies, considerable amount of space. So one of the things that active research is on is how can you shrink this? How can you make it smaller, make it more energy efficient, space efficient? The kinds of companies that are working on these are, of course, IBM, Google, Rigetti, and the dot dot dot. There are a whole bunch of others that are working on it as well. The once you get into the nitty-gritty details, whether depending on how the energy is distributed between the Josephson junction and the capacitor that is next to it, you can the Josephson junction, the capacitor next to it, that defines whether it's a transmon or mergemon and fluxonia, other devices that are other kinds of qubits that are designed in using superconducting materials. Here's a picture of one of the most recent works that used 300 millimeter wafer scale out of IMEC in Belgium, or EMEC in Belgium. They use aluminum-based Josephson junctions. And here is the work that we are leading at NY Creates, where we use tantalum-based materials to create the Josephson junction. Our feeling is that this one is more thermally robust, more environmentally robust, more chemically robust than aluminum-based systems. Aluminum has got a melting point of about 660 degrees centigrade, whereas tantalum is above 3000 degrees centigrade. You can dip this in dilute hydrofluoric acid, nothing happens. This one, because of the dissolved oxygen in there won't be any aluminum left. So you need to be a lot more careful when you make aluminum-based Josephson junctions than we think will be needed to be done when you use tantalum-based Josephson junctions. And this is what we are actively working on. In this section, so now we have talked about the various kinds of qubits that can be made with different kinds of materials, matter, or photons. Now I want to take the next few minutes to talk about the applications, if you will, the quantum computing, quantum networking, quantum sensing. So for quantum networking, right? I mean, here is a quantum internet that has been created on Long Island. It goes from Brookhaven National Lab out here through Stony Brook and all the way to New York City, where Connect is based. And I must say that this is the brainchild, or thanks to the work led by Eden Figueroa and many other colleagues at Brookhaven and also at Yale. They are thinking of doing a free space connection across the Long Island Sound going up to Connecticut here. So there are quantum networks on land, but in addition, quantum networking is there in space as well. And this is the one from a long time ago now, the Messias satellite that China launched, that is used for quantum key distribution, QKD. And here is the European first satellite that is going to be launched, I think, soon, for quantum key distribution. I mean, and by choosing to highlight China and Europe, my point is to say that, we are not alone in the United States in working on this, but clearly Boeing and HRL in September of next year will be launching the Q4S, Quantum for Space, I think, satellite that will demonstrate how entanglement happens in photon-based entanglement happens in outer space. But that is barely the beginning of what can be done in terms of quantum networking in outer space. More about that later. Quantum sensing is another area where the exquisite sensitivity of quantum objects to environmental perturbations is actually leveraged. So you're making lemonade out of a lemon, if you will, right? In quantum computing, you want to try and protect the quantum state so that you can make it do computation, and you don't want to allow it to get interfered by the environment. Whereas here in quantum sensing, you use that sensitivity to create new opportunities. And this is a paper from a group out at Berkeley. You can see the Lawrence Berkeley labs up on the hill. And what they did was to take an atom interferometer and use that to map the gravitational attraction as they went from downtown Berkeley up onto the hills, right? And what is amazing, I mean, this is fascinating to me, that you can see that they were able to sense the tide coming in and out of the bay in San Francisco Bay. So, their measurements of the gravitational increase using the device that they were transporting not only showed how allowed them to measure the average density of rock here, but they also were able to sense what is happening in the bay nearby as water flowed in. Why is this important? I mean, way back when I was trying to find the picture, but I couldn't. There was an article in The Economist about how you could use such sensing to see whether or not you've got salt domes under the earth. You could use it to find whether there are tunnels that have been built under the earth in order to, see them more clearly. Or if you're able to, sense the gravitational field you can also use it to navigate in a GPS denied environment, for instance, right? Because you have a clear sense of what the Earth is like, what the gravitational field can be like. There was a beautiful presentation from somebody from the Air Force where they mapped the Monterey Bay Canyon by flying across it in order to sense what is going on. A quantum diamond microscope uses the NV center, the nitrogen vacancy center. We didn't talk about that kind of qubit at all in the prior two pages, but this can be used to sense the electrical magnetic fields and use that to map maybe even the Earth's magnetic field or brain injury imaging, as you can see here. You can use it for research, and so a whole range. Oh, by the way, another example of monitoring what is happening gravitationally is you could monitor volcano activity using quantum sensors. So the possibility is enormous. The other thing, this is from a DARPA project where they are able to use a single atom, an atom that has been excited to a high energy state, in order to receive a whole range of frequencies with just one device, right? And with so the ability to be very sensitive, um, uh, thanks to the quantum object. This, for instance, could be utilized, or variants of this could be utilized to sense maybe a submarine that is under the ocean. You're looking at what is the modulation of the Earth's magnetic field due to the metal of the submarine, for instance. So all of these leverage the quantum object in order to sense fields, electromagnetic fields. Another thing is, maybe in the interest of time, let me skip past this, but quantum imaging is a whole new and amazing field. Quantum computing, where we are now, right? So here is a recent paper, November of this year, from IBM, showing that they had entanglement in a set of 120 qubits, creating, surpassing the required minimum threshold of fidelity. Barely surpassed it, but clearly, it's been done. Here is Rigetti that has demonstrated a system of four 9-qubit chips that were able to demonstrate qubit error, 2-qubit gates. Here is Google's Sycamore quantum computer. And the reason I brought this up is not only to show the scale of what is involved now, but to show the opportunity, right? This Python-sized cables that are coming out of the quantum computer should be made smaller. And that is an active area of research that many people are working on, supported by funding from the US government. So talking about what the US is doing, clearly there is no question that US is leading in their effort, but thankfully we're not standing still. Recently, just in the past month, the US Department of Energy announced that it was starting the next 5 years of the quantum information science research centers, five of them that were started when the National Quantum Initiative Act was signed 5 years ago, 2018, and then we started now. And of course, here is how the DOE is working on quantum in space with a whole range of partners, including IonQ, Honeywell, and so on, Axiom Space, Boeing, in order to deliver quantum in outer space. This is a recent announcement of the Genesis project from the DOE, where the idea is that the Department of Energy will create a confluence, a collaboration of all of the 17 national labs that are present under the DOE, along with other partners, in order to train advanced AI that also brings in quantum sensing, simulation, and the data, both for scientific exploration and for commercialization. So this, like I say, the ferment of energy is continuing to rise. DARPA, we all know, has been working on supporting quantum research for a long time. The most recent one is, of course, the Quantum Benchmarking Initiative led by Joe Altepeter. And recently they announced that 11 companies had made it past the stage A into stage B. And you will recognize Dirac, of course, IBM. Nord Quantique is based in Canada, and we signed an MOU with them to say that we'll be working together. You will recognize Xanadu that I mentioned before. So so DARPA is recognizing that there is a whole range of technologies that need to be explored, and all of them are capable of scaling, right? That is what distinguishes the aspects of this QBI. Many other projects that DARPA is highlighting, all the way from, and this is the most recent one that people are still responding to. And I like the statement, we want to move beyond the one qubit to rule them all approach. I mean, yes, I love Lord of the Rings, and I'm glad to see that. And my feeling is that now is not the time to say which is the qubit that will win, right? Because there are unique strengths and weaknesses for every kind of qubit. And the best way is to create a heterogeneous architecture so that you can leverage the best of all the worlds. Maybe you use trapped ions for memory, quantum memory, and you're using photonic quantum to connect a quantum system in New York with a quantum system, hundreds of miles away. So, and then you've got synthetic quantum structures that are being led, quantum sensing of neutrinos. Of course, neutrinos are these ghostly particles that pass through, millions of which pass through our bodies every second. We don't sense them because they don't interact with anything. But here's an example of how DARPA is working on a project to enhance the sensing of neutrinos. And again, here's another example of how quantum is not going to exist in and of itself. An integration of quantum and classical systems are important both for computing as well as for networking, right? And so the announcement some weeks ago saying that NVIDIA, no, sorry, AMD and IBM will be working together on a quantum classical hybrid sort of makes sense, right? And we all know NVIDIA's CUDA approach that is being utilized for quantum as well. So, the clearly there is a lot of work that is happening. U.S. government research labs, we know from MIT Lincoln that they are generating what are called candle qubits. These are perfect qubits that they have characterized. And so when you characterize them, if you get the same results, you know that at least your measurement system is not worse than what it should be in order to recognize the quality of the qubit. LPS in Maryland has a collaboratory where they are working with a variety of people across the US. And literally, this is a nice new term. It doesn't exist in the dictionary, as Sardashi likes to say, but it conveys the intent that we collaboration and in quantum research is important. AFOSR has a MQC project where it is looking at a variety of quantum devices and trying to move from merely trying to say what is the best qubit to be made to understanding the correlation and causation from the materials aspects in order to make better qubits. Here is a chart from Dr. Michael Haydock of AFRL Rome, where he was pointing out, that you could have quantum systems in outer space that are doing, times distributions as well as detecting tunnels, like I was talking about. So, whole rate. The whole range, excuse me, the whole range of quantum sensing, quantum networking, quantum computing that is in AFRL's interest. And here are examples when it comes to photonics that AFRL Rome has been working on in close partnership with NY Creates, if I may add. So this quantum wafer is fabricated at Albany, and it has these various devices. We have a strong partnership, of course, with RIT, and this program, this is through AIM Photonics, is delivering a quantum PDK very soon for people to design into. I'll talk more about the PDK soon. NSF, there is a whole range of quantum leap challenge institutes that NSF has been creating across the U.S. With significant funding. So where are we now? And I want to hark back to the Nobel Prize. This is an old paper by John Martinez where he was pointing out that in a crystalline system, you got a very clean energy space. Nothing is interfering with your quantum system. But if you got an amorphous material, you have all of these defect states that tend to rob energy from the qubit or cause decoherence in phase to the qubit. And so a lot of the active work is trying to figure out how to eliminate these TLSs or engineer them out of the system. Clearly, yes, RSA encryption breaking was the first thing that we started talking about when quantum computing, when Shor's algorithm was discovered, invented. But you need 1,000,000 qubits, and we are far, far away from the 1,000,000 qubits. And this is part of the scaling that is where we need to go now. And I don't mean to suggest that all of us should go to Illinois and for this quantum park, but it is a great example of the kind of collaborative research and the infrastructure that is needed. This space is going to be used by PsiQuantum. This is on the shores of the lake, one of the Great Lakes, right? And Illinois is investing a large amount of funding in that. New York State is also formulating a similar thing in the tri-state area. There is a quantum alliance that has been launched with similar goals to allow people to work together to scale quantum systems, getting commercial entities, working with labs, working with academia. How are we going to do that? I want to, I'm getting to the very end, but the main point is the process design kit, right? This design kit is an idea that was developed in the 1970s for the semiconductor industry. And that, in my opinion, was central to why the IC industry is now, a $1 trillion industry across the world. And why is it so powerful? Because if you say, oh, I want to build a data center like this, there isn't anybody in the world that knows every single thing about this data center. There are people that know how to put these computers together. They rely on somebody else to design the quantum computer, or the chips that go into such a data center. The person that designs this chip perhaps doesn't need to understand the nitty-gritty details of the electronic circuits of a gate, right, or inverter, and so on, or an SRAM. And then the person that designs this doesn't need to understand the basics of the material science that goes in to create this, to fabricate this chip. But each layer creates a model that says, here's my promise to you. And here is when you tell me you want this and I'll do this, it will perform as intended. And that allows for this sort of chain to be created. That's what quantum can and should do. It should adopt it, but clearly the challenges for quantum are far more. So, which is why I want to say you should adapt that mindset and apply it to quantum. Quantum algorithms is another thing that needs to be worked on in order to make sure that there are more use cases, more of a demand pull from the economy to find new ways in which quantum can speed up. Because clearly, at this point, we have 3 or 4 algorithms that are extremely good. If you like, you can go to this quantum algorithm zoo and then look at all the algorithms that are present there. And clearly, there are people that are working on discovering and inventing new ones. So I'm getting close to the end. I want to say, it's true that we are at the beginning of things that we cannot even imagine. I think it is true that no technology, the impact of the technology over the long term has always been underestimated. The whether it's railways or any others. So anyway, so I will continue with that, please. With that, let me stop. I want to just turn off my
Thank
phone.
you, Pops, for that great presentation. Questions are coming in. If any of the attendees have questions, please type them into the Q&A box, and we'll try to get to as many as we have. We have a few minutes left over. So let me just go through this list. Can you define quantum error correction? Is quantum error correction a bottleneck for increasing the number of qubits that can be used in quantum computers?
Oh, that's a very good question. And the reason quantum error correction is critically essential is because a quantum object gets attacked, if you will, by the environment. And so it is going to change its state. Part of the effort is to make sure that the quantum object stays in its quantum state without being affected. But the minute it is affected, if you had a way to correct that error, then you would be able to move forward. And so quantum error correction, the innovation that came up early on was one of the critical things that said, well, we don't need to make perfect quantum objects because we can always detect it and correct it. The name of the game now is, can you minimize the rate at which these errors creep into the system? And can you design a hardware system and an error correction algorithm that is efficient enough so that you don't have to so that you get ahead of the wolf chasing you, right? So if you the way in which quantum error correction, in simple-minded words, is you think of a bunch of qubits that are working together in order to form one logical qubit. So the more powerful your error correction algorithm is, the overhead that is required. Do you need 1,000,000 qubits to create one logical qubit, or do you need 1,000? Do you need 10,000? So that is the progress that quantum error correction allows you to leverage. The progress is made both in the computational space with new error correcting codes, quantum error correcting codes, as well as in the hardware. Because as the hardware becomes capable of having longer coherence times, your error correction becomes less and less important. You need smaller overheads. Hopefully that explains. Yeah.
Another question. How can quantum technologies be effectively integrated into industrial processes so that we generate measurable value in more immediate terms with more practical results? I think your process design kits, I think, tie into this idea.
Yes, yeah, I mean, one aspect is when you talk about quantum computing, scaling is important. When you're talking about, sorry, this person is really trying to reach me. When you talk about quantum sensing, you need to make sure that this system is engineered in a way that is field deployable. So when I said, okay, these people at Berkeley were able to get their atom interferometer into the back of a truck. In fact, their paper has got a picture of that truck and drive it up the road. You need to make sure that it can be deployed in a small enough and robust enough package so that it can be used. So for quantum sensing, the implications for broad use is the system level integration, and there are companies that are working on that. There's a company in out of Maryland that is working on these sensors to sense magnetic and electric fields. Imagine if you didn't have to sit. I'm sorry. I'm claustrophobic. I could not sit long enough inside those MRI machines before I wanted to be let out. But if you had a quantum sensor, suddenly everything will be different. You will not need to sit in a superconducting magnet. Earth's magnetic field, you'll be able to sense.
Um, do you see any need for a national strategy in electronics or in semiconductor manufacturing to support advances in quantum computing?
Yes, and in some ways, in many ways, I think you can say that the nation has already embarked on that strategy. To make sure that the fabrication of electronics happens onshore. And the nice thing about all of the aspects of scalable quantum that I'm talking about, when it comes to photonics, when it comes to superconducting qubits, and even ion traps, they utilize the fabrication techniques that the semiconductor industry has polished over the past 6 decades now. So, as the semiconductor industry revitalizes itself inside the US, it'll mean that much more opportunities for those very same fabs to be utilizing that for quantum. For instance, PsiQuantum is working with Global Foundries in Malta on making their quantum computing chips. So there is a synergy there between the two. And yes, it needs long, patient capital. I think that's what the nation can provide the industry.
Okay, last question would be, you had a slide that said the US is leading, but not standing still. Who else is close, and is anyone catching up?
Clearly, China is doing things that some of which we don't even know. I remember in 2019, they announced a $150 million effort to create a superconducting digital logic. And then because I'm personally interested, I was trying to see what happened, didn't hear anything about it. But clearly, Europe is, at least in Europe, we are talking with a friendly nation. There is a strong Europe-wide effort. They've got a quantum flagship program. Britain has got a strong effort in quantum as well, out of Oxford and Heriot Watt University and so on. So everybody is running, but I do think that we are ahead. And like I said, I'm glad that we are not standing still. We're not resting on our laurels. We're continuing to push ahead.
Okay, I'm going to ask one more because I like.
Please.
What would you guess is the ratio of quantum to classical computers, I guess out in the world or in the government, in 15 to 20 years?
Oh, wow. I like this. If I put on my optimistic hat, I think quantum. I mean, okay, let me take one step back and say it is not so much of a ratio where quantum will replace the classical, right? I mean, we are thinking of a world where the two need each other, where the quantum and the classical coexist. But the number of quantum computers that are going to be present is going to increase by orders of magnitude. I will go be as bold as that and say that we're talking about maybe 20 to 30 quantum computers. Now there will be 3,000, but
And we
summit will
won't
also
know the
increase.
difference, right? Things will be processed for us by services, and some of them may be processed by quantum machines.
No, that is very insightful. You're right, Arun. I mean, and I didn't mention that, right? I mean, so AWS and many other companies have these systems whereby you can go put your quantum thing on a cloud. And IBM also does. You put your query on a cloud, and it gets executed on a quantum system of your choice. Or in the fullness of time, it'll be, I don't really care where it is computed. There will be a quantum accelerator that is pulled in to accelerate certain aspects of the computation that need quantum and feed back into classical and vice versa. So you're exactly right. And AWS is already doing that. They have their compiler that can say, use IonQ's system, use this, use that. So they're already doing that.
Okay, with that, we are really out of time, and I want to thank you, Pops, Dr.
Thank
Paparao,
you.
for this great presentation and answering those questions. I want to thank everyone for their attendance and submitting those questions. If you have feedback about this event, especially topics you'd like to see us cover in the future, please email us at eti@ndia.org. I want to take this opportunity to highlight a few of our upcoming ETI events in the new year. We will not be hosting a Tech 101 webinar in January, but we do have two exciting webinars you will not
Well,
want to miss on January 22nd, 2026 from 2 to 3:30 p.m. We're going to be hosting a webinar called Beyond the Spark, the Holistic Business Case for Robotic Welding.
wow.
And then on January 28th, 2026, from 1 to 2 p.m., we're going to kick off our new four-part webinar series, Digital Transformation for Acquisition. This will be webinar one of a series of four. Our next Tech 101 will be in February, so be on the lookout for that. It's going to be on Agentic AI. Look out on
Wow.
NDIA's website calendar events for more information. To register for these and other ETI events, please visit www.ndia.org/events. Thanks again to Pops, and thanks again to
Thank
everyone for
you.
joining us today.
Thank you. My thanks as well. Thank you so much, Aaron.